Dear friends, welcome in the class of mathematics. In last lecture, we have seen rule 1 for finding integrating factor and its examples. Today, we have to see rule 2 for finding integrating factor. Rule 2, if the differential equation m dx plus n dy equal to 0 is of the type y into f1 of xy dx plus x into f2 of xy dy equal to 0, then integrating factor is 1 upon mx minus ny, provided mx minus ny not equal to 0. Here f1 and f2 are functions of x and y, means in every term of f1 and f2, degree of x and degree of y is the same. Now we have to see the proof of this rule. So proof, given that the differential equation m dx plus n dy equal to 0 is of the type y into f1 of xy dx plus x into f2 of xy dy equal to 0. We can write this equation as m dx plus n dy equal to 0. So comparing coefficient of dx and dy, we get m is equal to y into f1 xy and n is equal to x into f2 of xy. To show 1 upon mx minus ny is integrating factor, so multiply 1 upon mx minus ny with given differential equation 1, we get y into f1 of xy upon mx minus ny dx plus x into f2 of xy upon mx minus ny dy equal to 0. That is, say this is m1 and this is n1, so we get m1 dx plus n1 dy equal to 0, and therefore m1 is equal to y into f1 of xy upon mx minus ny and n1 is equal to x into f2 of xy upon mx minus ny. Now put here values of m and n, so we get m1 is equal to y f1 xy upon y into f1 xy into x minus x into f2 xy into y. Here, both the term contains x into y, so take out xy as a common from denominator, and so we get y into f1 xy upon xy f1 xy minus f2 xy. Here y get cancelled, and so we get m1 is equal to f1 xy upon x into f1 xy minus f2 xy. Similarly, we can write n1 as f2 xy upon y into f1 xy minus f2 xy. For sake of simplicity, we can write f1 of xy as only f1, and so we get m1 is equal to f1 upon x into f1 minus f2, and n1 is equal to f2 upon y into f1 minus f2. Now we have to show this new equation 2 is exact. So for that, we have to find derivative of m1 with respect to y and derivative of n1 with respect to x. So differentiate on both sides partially with respect to y on the both sides of this equation, we get dabba by dabba y of m1 is equal to dabba by dabba y of f1 upon x into f1 minus f2. Here 1 upon x is a constant, so take outside of that derivative, and so we get dabba m1 by dabba y is equal to 1 upon x dabba by dabba y of f1 minus f1 upon f1 minus f2. But you know, f1 means it is f1 of xy, f2 of x, f2 means f2 of xy, and so we get dabba m1 by dabba y is equal to 1 upon x dabba by dabba y of f1 of xy upon f1 of xy minus f2 of xy. Here we have to find partial derivative with respect to y. Numerator as well as denominator contains y, so we should use derivative of u upon v formula. And so dabba m1 by dabba y is equal to this 1 upon x as it is. First take derivative of f1 of xy with respect to y, which is f1 dash xy into derivative of xy with respect to y, which is x. So derivative of u, v as it is, that is f1 xy minus f2 xy as it is, minus, now u as it is means f1 xy as it is, derivative of v, that is first derivative of f1 of xy, which is f1 dash xy into derivative of xy with respect to y, which is x, and so which is f1 dash xy into x minus derivative of f2xy with respect to y, which is f2 dash xy, and then derivative of xy with respect to y, which is x, and divided by v square, means denominator square. So we get here f1xy minus f2xy bracket square. Here both the term contains x. First term contains x, second term also contains x. So take out x as a common from numerator, and da by m1 by da by y is equal to x upon x f1 xy into f1 dash xy minus f2 xy into f1 dash xy minus f1 dash xy into f1 xy plus f2 dash xy into f1 xy upon f1 xy minus f2 xy bracket square. Here x get cancelled, and therefore da by m1 by da by y is equal to f1 xy f1 dash xy minus f2 xy f1 dash xy minus f1 dash xy f1 xy plus f2 dash xy into f1 xy upon f1 xy minus f2 xy bracket square. Here this first term and the third term get cancelled. f1 xy f1 dash xy f1 xy f1 dash xy positive and negative get cancelled, and so we get da by m1 by da by y is equal to minus of f2 xy into f1 dash xy plus f2 xy into f1 xy upon f1 xy minus f2 xy bracket square, and therefore da by m1 by da by y is equal to f2 dash xy into f1 xy minus f2 xy into f1 dash xy upon f1 xy minus f2 xy bracket square. We can write this as da by m1 by da by y is equal to f2 dash into f1 minus f2 into f1 dash upon f1 minus f2 bracket square, and therefore da by m1 by da by y is equal to f1 into f2 dash minus f1 dash into f2 upon f1 minus f2 bracket square. Similarly, we can find da by n1 by da by x as f1 into f2 dash minus f1 dash into f2 upon f1 minus f2 bracket square, and therefore both these values are same, means partial derivative of m1 with respect to y and partial derivative of n1 with respect to x both are same, and therefore new differential equation 2 is exact. We multiply that equation number 1 by 1 upon mx minus ny, we get a second equation, and that second equation is exact, means 1 upon mx minus ny is an integrating factor of the differential equation 1. That is the proof of that rule. Now we have to see some examples on the rule. Examples. Solve 1 plus xy into y dx plus 1 minus xy into x dy equal to 0. Solution. Given differential equation is 1 plus xy into y dx plus 1 minus xy into x dy equal to 0. This is equation number 1. This is the equation of the type m dx plus n dy equal to 0, and therefore m is equal to 1 plus xy into y, n is equal to 1 minus xy into x. Given differential equation is of the type f of xy y dx plus f of xy x dy equal to 0. That is f1 xy y dx plus f2 xy x dy equal to 0. And therefore integrating factor of this given differential equation is given by if is equal to 1 upon mx minus ny. Now put the values of m and n here. So this is equal to 1 upon 1 plus xy into y into x minus 1 minus xy into x into y. So this is equal to 1 upon, take this xy inside 1 and this xy inside and minus sign inside 1, we get if is equal to 1 upon xy plus x square y square minus xy plus x square y square. Here we observe that plus xy minus xy get cancelled, and so if is equal to 1 upon x square y square plus x square y square, means it is 2 times x square y square. So this is the if. Now multiply this if with given differential equation 1, we get 1 plus xy y upon 2x square y square dx plus 1 minus xy into x upon 2x square y square dy equal to 0. Here in first term y get cancelled, in second term x get cancelled. So we get 1 plus xy upon 2 x square y dx plus 1 minus xy into x upon 2xy square dy equal to 0. This is equation number 2. So this differential equation is of the type m dx plus n dy equal to 0. So value of m is 1 plus xy upon 2x square y, and value of n is 1 minus xy upon 2xy square. Now separate the geometry here. So you get m is equal to 1 plus xy upon 1 upon 2x square y plus xy upon 2x square y, and n is equal to 1 upon 2xy square minus xy upon 2xy square. Here we observe that y get one x get cancelled, y get cancelled, and similarly here x get cancelled, y get cancelled. So we get value of m is 1 upon 2x square y plus 1 upon 2x, and n is equal to 1 upon 2xy square minus 1 upon 2y. So these are the new m and n. We know equation 2 is obtained by multiplying integrating factor. So differential equation 2 is exact. As this differential equation 2 is exact, its solution is given by integration m dx keeping y as a constant plus integration terms in n not containing x dy equal to constant c, it is c dash. Now put the values of m and n here, and so we get integration 1 upon 2x square y plus 1 upon 2x dx keeping y as a constant plus integration terms in n not containing x. N contains two terms. First term contains x. So don't write first term, rather only second term. So it is minus 1 upon 2y equal to c dash. Now we have to evaluate these two integrals. Here y is constant. So 1 upon 2y is constant. So take outside of that integral. So we get 1 upon 2y integration 1 upon x square dx plus in second integral here 1 upon 2 is constant. So take outside of that integral. So 1 upon 2 outside, integration 1 upon x dx. Then in third integration minus 1 upon 2 is constant. Take outside of that integral, integration 1 upon y dy equal to c dash. Integration of 1 upon x is log x, integration of 1 upon y is log y, integration of 1 upon x square is minus of 1 upon x. And so we get 1 upon 2y minus 1 upon x plus 1 upon 2 log of x minus 1 upon 2 log of y equal to c dash. Take this 1 upon 2y inside 1, and so we get minus 1 upon 2xy plus 1 upon 2 log x minus 1 upon 2 log y equal to c dash. Now multiply all this equation by 2, and so we get minus 1 upon xy plus log of x minus log of y is equal to 2c dash. We multiply each and every term by 2. I use your formula log of a minus log of b. It is log of a upon b, and so we get minus 1 upon xy plus log of x upon y equal to 2c dash. So this is c. So this is equal to c. Now we observe that this is a relation between x, y and constant. So this is the general solution of the given differential equation 1, which is the final answer. Now move to the second. Solve xy plus 2x square y square into y dx plus xy minus x square y square into x dy equal to 0. So given differential equation is xy plus 2x square y square y dx plus xy minus x square y square into x dy equal to 0. Denote this as equation number 1. This equation is of the type m dx plus n dy equal to 0. So comparing coefficient of dx and dy, we get m is equal to xy plus 2x square y square into y, and n is equal to xy minus x square y square into x. This given differential equation 1 is of the type, this is the function of x into y. This is again another function of x into y. So you can say this differential equation is of the type f1 x into y y dx plus f2 x into y into x dy equal to 0. And therefore, by that second rule, integrating factor is 1 upon mx minus ny. Now put the values of m and n here. So we get 1 upon value of m, which is xy plus 2x square y square into y into x minus value of n, which is xy minus x square y square into x into y. Now take this xy inside 1, this xy inside 1 and minus n inside. So this is equal to 1 upon x square y square plus 2 x cube y cube minus x square y square minus minus plus x cube y cube. Here we observe that plus x square y square and minus x square y square get cancelled. So this is equal to 1 upon 2x cube y cube plus x cube y cube. So it is 1 upon 3x cube y cube. So this is the integrating factor. Now multiply this integrating factor with the given differential equation 1. We get xy plus 2x square y square into y upon 3x cube y cube dx plus xy minus x square y square into x upon 3x cube y cube into dy is equal to 0. This is equation number 2. Here we observe that in first term y get cancelled and in second term when x get cancelled. And so these are the new m and n. Take out y as a cancel here and x as a cancel. And so m is equal to xy plus 2x square y square upon 3x cube y square, and n is equal to, here x get cancelled, so xy minus x square y square 3x square y cube. Now separate the denominator here. So m is equal to xy upon 3x cube y square plus 2x square y square upon 3x cube y square, and n is equal to xy upon 3x square y cube minus x square y square upon 3x square y cube. Here in first term x and y get cancelled, in second term x square and y square get cancelled. So m is equal to 1 upon 3 x square y plus 2 upon 3x, and similarly in n, here xy get cancelled, so it is 1 upon 3 x y square minus, here x square y square get cancelled, so here we get 1 upon 3 y. As this differential equation 2 is obtained by multiplying integrating factor, so this differential equation 2 is exact. As this differential equation is exact, its solution is given by integration m dx keeping y as a constant plus integration terms in n not containing x dy equal to constant c. Now put the values of m and n here, and so we get integration value of m, which is 1 upon 3x square y plus 2 upon 3x dx keeping y as a constant plus integration. Now see, n contains two terms. First term contains x, so don't write first term, rather only the term which doesn't contain x, that is minus 1 upon 3y dy equal to c. Now separate this integration. Here 1 upon 3y is constant, so take outside of that integral. In second integral 2 upon 3 is constant, so here we get 2 upon 3 outside, integration 1 upon x dx. And in third integration minus 1 upon 3 is constant, take outside of that one, so we get here minus 1 upon 3 outside, integration 1 upon y dy, and that's c. So we get like this. You know, integration of 1 upon x is log x, integration of 1 upon y is log y, and integration of 1 upon x square with respect to x is minus 1 upon x. And so we get 1 upon 3y minus 1 upon x plus 2 upon 3 log of x minus 1 upon 3 log of y equal to c. So you can write this term as minus 1 upon 3 xy plus 2 by 3 log x minus 1 by 3 log y equal to c. Now multiply whole this equation by 3. So we get minus 1 upon xy plus 2 log x minus log y is equal to 3c. Transfer this 2 to the power of x, and so we get minus 1 upon x log of x square minus log of y equal to 3c. Now use the formula here, log of a minus log of b is equal to log of a upon b, so this will become log of x square upon y, and so we get minus 1 upon xy plus log of x square upon y equal to 3c. So log of x square upon y minus 1 upon xy equal to 3c is the general solution of the given differential equation 1. This is your final answer. Thank you.